I'll finish off this last example on reactions, bending, moment of inertia, second moment of area, and bending stress. Then I will introduce project 3 to you all. And then if there is time, we will start on deflections. Pardon? Project 2 I've already told you all about. Well, Project 2 is happening next week on the Wednesday lecture time slot. So next Wednesday, this will all be full. It will be heaving. And you have to come to get your mark for it. So if you cannot come, you need a valid excuse, a medical certificate or something like that. So you need to come to be present at the bridge testing to get your mark. Okay, let's get going on this. So with this next problem, the question asks, well, the question tells you that the section comprises a steel plate here, welded to a CHS, which, if you don't know, is a circular hollow section. I can't spell. And it's loaded as shown. They give us the yield stress of 750 and the yield stress for the circular hollow section. So they are both different. And the question is, will the section fail? So we would be doing an ultimate limit state design here. So once we draw our bending shear force diagram, we then need to use our bending stress formula, My and I. So let's get going on this one. First thing we need to do before we can draw our shear force diagram is calculate our reactions. And looking at the unknown reactions here, you will see that we have 1, 2, 3, and of course that's a fixed support, 4 unknown reactions. But once again, we won't panic because we have an internal pin. So that internal pin gives us our 4th piece of information that we can then calculate our 4 reaction forces with. So what do we need to do in this instance? As usual, we need to split our system into 3 free body diagrams either side of the internal pin. So I'll redraw the 2 free body diagrams slightly apart with my load, with my unknown reaction. I'll call it PY and PX. PX, PY. When you draw them either side of the pin, remember you draw them equally and oppositely. So which side would we start with, the left or the right? You have to start with the free body diagram where you only have your 3 unknowns. So we would therefore start by looking at this right-hand side. So looking at the right-hand side, all the forces in the x direction equal 0. So 10 minus px equals 0. So we know the horizontal force passing through the pin is 10 kilonewton. So I'm now just going to scribble that out and call that 10 kilonewton. And then I'm also just going to draw this reaction, horizontal reaction, in the direction it occurs, 10. So now we have horizontal equilibrium. So moving back to my free body diagram on the right now, I know the 2 forces in the y direction equal 0. That's not telling me anything, however. So I'm going to take moments next, and I'm going to take moments at the pin. And doing so will help me calculate CY. So that's 1 metre. Both distances are 1 metre. So taking moments at the pin, anti-clockwise being positive, I would have minus 10 times 1 is my moment caused by my horizontal force. And my CY causes an anti-clockwise moment about the pin. So that would be plus CY times 1. And from that, CY would equal 10 kilonewton. And I don't have room here. Oh, well, I'll squash it in. If I now do all the forces in the Y direction, we then have the force at the pin is minus 10 kilonewton. So up here, I'll say we now know CY is equal to 10 kilonewton. And we said this AX value, well, that's equal to minus 10 kilonewton, which means it's going the other way. So we still have the AY to derive and AM, the moment, reaction moment, to derive. So at this point in time, you have two options. You could now move to the free body diagram on the left-hand side, or you can go back to looking at the system as a whole. Because if you come up here and look at the system as a whole, the free body diagram of the system as a whole, you now only have your two unknowns. So you could solve for AY and solve for AM. But what I will do is I will move to my left-hand side free body diagram. We said PY, this force here, is actually a downward force of 10. So therefore, that means this force here, when we move across, is an upwards force of 10 kilonewtons. Can everyone see that? And I'll scribble that out. So now I have my unknown pin forces as known values, and I treat them as if they are now loads applied. So now, when I look at all the forces in the X direction, in the Y direction, I have my AY minus my UDL load and plus my pin load of 10. Excuse me. Equals 0. So from that, I get AY is equal to 5 kilonewtons. And now the final thing I have to calculate is my moment, reaction moment, AM. So I'll now take moments at A. And I do, of course, have my AM. That's what I'm trying to calculate. It's a moment. It's going anti-clockwise. Then I would subtract the moment due to my uniformly distributed load, because that's going clockwise. I would add the moment due to my pin, vertical force. And the horizontal force, because you can trace that point load straight back to A, causes no moment. So from that, we get a value of minus 7.5 kilonewton meters. Why is it 10 times 3? It's this 10 force here. Yeah. Is that okay? Yep, okay. So I'll move that information now onto the next slide. So over here, our reaction forces are 5 kilonewtons up. The horizontal was negative, so I'll draw it in the direction it occurs in. Now when we calculated that moment, can you see here it was minus 7.5? So that minus means opposite to the direction I had it drawn in. So therefore my moment here is actually clockwise. And then I have my reaction here of 10 kilonewtons. So now what we need to do is draw the shear force diagram and the bending moment diagram. Can I give you 2 minutes based on those reactions? To try and draw those two. Also, I'd like you to attempt to draw the deflected shape. So remember a shear force diagram? You start at the left-hand side and you follow the loads. When your beam is horizontal, you are plotting the forces in the y direction. When your beam is vertical, you will be plotting the forces horizontally. So what I'll draw here is an eye here, just to indicate when you come and draw your shear force diagram, you'll be looking at it from where the eye is. So I'll draw this part for you. So you would start at the left-hand end, which would be the top. You would step up a value of 10, move constantly down, and then because of this 10 reaction here, that would return to 0. Ooh, I'm accidentally pressing this button. The table's moving on me. Ooh, that's cool, isn't it? Freaked me out a bit, though, to find it suddenly going up. Sorry, I'm distracting you. Shear force diagram, bending moment diagram. Shear force shouldn't be too much of a problem. We start at the left-hand end and we follow the loads. Where there is no load occurring, you move constantly across. If you have a uniformly distributed load, it reduces uniformly, linearly. Now I feel really short now, the table's really high. How high does it go? Don't tell anyone if it falls out. No, that's it. I feel like an Oompa Loompa. Ooh, that was a bit rocky coming down. Go on, give it a go. Shear force diagram, bending moment diagram. You all got it popping up a value of 5. Then it's going to reduce linearly by 15. So that's going to come down here. Please do have a short ruler with you in the test and the exam and in general. To 10. Nothing happens, so I just move horizontally across. Oops. And why is this popping up? Because of my reaction here, 10. So this line is basically telling me all the forces in the y direction equal 0. And in effect, this line is telling me all the forces in the x direction equal 0. So the shear force diagram is a plot of perpendicular force. Oops, I took the whole thing away. Now the important thing to remember, your shear force diagram is your shear force diagram, but it's also the slope or the gradient. The value here of 5 is telling me the slope of my bending moment diagram has a value of 5 at that point. At this point here, what is the slope of my bending moment diagram? It's 0. So that's telling me I have a maximum. So when V is 0, my moment, it's either a maximum or a minimum. Now, remember we plot positive down when we do our bending moment diagram. So a positive shear force equates to a downward slope. Just remember that. Positive downwards. So I look at my shear force in here, it's positive, so my bending moment will be sloping down. My shear force in here now is negative, so my bending moment is going to slope up. My shear force through here is still negative, it's going to slope up. Now when you come and look at the vertical component, the easiest thing is to rotate your pages round or to rotate your head that way and say I have a positive And a positive is a downward slope. So there's my downward slope. See that? Okay. Now we know what direction our bending moment is sloping in. Where is our bending moment equal to 0? At B. What's the value of my moment? 0. At the internal pin, what are the internal bending moments equal to? 0. So my bending moment is 0 here. At this fixed support, what's my moment equal to? Good, you're not saying 0. Okay. So the question is now, is it plus 7.5 or minus 7.5? The way I look at it is I say, okay, this is my reaction moment. 7.5 is my reaction moment. And the moment just to the other side of that is equal and opposite. So there is my internal moment. So my internal moment for moment equilibrium is 7.5. And those two moments as applied, what are they doing? They're creating a happy face. So that is a positive. There is a positive moment in there. Thus, the moment here is 7.5 because we draw positive down. Do you reckon you could do the rest of it? When my shear force is constant, what's my bending moment? Linear. When my shear force is linear, what's my bending moment? A parabola. Only thing I can do now is, this is all linear, so my bending moment is a parabola. The slope is getting smaller and smaller and smaller, and then it's 0. So the only thing it can be doing is that. And then it gets bigger and bigger and bigger, and then it has to have a 0 value there. So there's my parabola. Then my slope in here, it's 0 here, so it must increase like so. And then I move to the other end. My bending moment is 0 here, so it must slope down. Now can you imagine that corner, see my two arms, flattening out? If I opened up that corner, would that point there join up with that point there? Yes, they would touch. So, what's the moment here? If I cut the beam here with 10 here, what's the bending moment down here equal to? 10 times 1? So the moment here is 10, and going round a corner, it has the same value. What I'm saying is when I cut a horizontal beam, you're quite happy that that moment equals that moment. When I cut round a corner, well, we're saying the moment on the horizontal leg equals the moment on the vertical leg. So they're also equal. So that 10 must equal that 10. We've got 7.5 here. All we're left to calculate now is that maximum moment there. So there are two ways you can do this. One is the area method, where we work out that area. In order to do that, we need to know that distance. How do we know that distance? Rise on run is equal to the slope, and we know that this slope here is the value of W. So if that's 5 kilonewtons per metre and that's 5, that distance in there, x must equal 1. And thus that area in there would equal 2.5 kilonewton metres. So does that make this moment here equal to 2.5? No, it's equals to 2.5 plus my 7.5. So that value there is your 7.5. I should change colour again now. So that moment there is 7.5 plus 2.5, which is 10 kilonewton metres. Now, if you are completely bamboozled with how I found that moment there, not a problem. What I would expect you to do would be to actually cut the beam 1 metre in, draw your free body diagram, which is your moment, your reactions, you would cut it 1 metre in, and then you would calculate the value of that moment. So you would use equilibrium. And doing so would give you a moment of 10. Okay, we have our bending moment. Why do we need our bending moment? Because our bending stress, maximum stress occurs where our my is maximum. So our maximum moment will either occur here in the corner where it's 10 or down here where it's 10. So far so good? Okay, so looking at our formula, we still have to calculate our moment of inertia, our second moment of area. And we will do that now quickly. For now, I'll assume my neutral axis sits within the plate. So now, which way have I done it? Y of the top. Let me do it the same way. 25, just give me a minute. Okay, I'm going to calculate Y from the bottom. Now, remember to find where the neutral axis is, we effectively divide our section up into areas. So that would be area 1 times Y1 plus area 2 times Y2 divided by my total area. So I'm going to refer to my circle as area 1 and my plate as area 2. So my circular hollow section, it's 50 mil diameter. So if it was solid, it would be pi r squared, pi 25 squared, but it is hollow. So then I would subtract from that. It is 2 mil thick. So from that I would subtract, do I subtract 21 or 23, everyone? Good. This is where people go wrong. And the distance to the centroid of that section, it's a 50 mil diameter, is 25 mil. Because I'm measuring distances from the bottom. My second area, very simply, is my 75 times 5. And I have to measure the total distance from the bottom to that centroid. So that distance would be 50, which is to the top of the circle, plus, I'll just write it as 75 on 2. Then we divide that by the total area. And we get a value out of here of 59.64 millimetres, which does place it above the circular hollow section. Any questions so far, or so far so good? So now, when we come and use our formula here, what is Y? Y is the distance from the neutral axis to the extreme fibres. Because remember, my bending stress distribution is triangular. So that distance in here, I'll call Y top, and that's equal to 65. And that distance in there is Y bottom, which is equal to my 59. So now I have to calculate my moment of inertia. It's a sum of all the individual i's about their own centroids, plus a sum of all the areas times their respective shifts. This is what people get confused by. So shift, let's move to a different colour again, purple. Shift is the distance between the section centroid, which is where I've drawn this dashed line, and the centroid of the rectangle. So that would be shift 2. So once again, what is shift? It's the distance between the centroid of your shape and the centroid of the overall section. So that would be shift 1. So when I work it out now, when I now calculate I as being a sum of all the i's, for the rectangular plate it's BD cubed on 12, so it is 5 times 75 cubed on 12. And for a circle, oops, I didn't mean to write pi, but that's okay because I can use my eraser. I for a circle is pi r to the 4th on 4, if you've forgotten. So for this shape here, because it's a hollow circle, it would be 25 to the power of 4 minus 23 to the power of 4 divided by 4. So this is a sum of all the moments of inertia about their own centroid. But we have to calculate about the parallel centroid. So to that we add on our area for our plate, which is 5 times 75, and that shift 2 value in here, when you work it out, works out to be 27. So please go over this yourself and make sure you know where it's come from. So where does it come from? The distance from the bottom to that top is 50 plus 75 on 2. So that's equal to, what's that, 87.5 minus my 59.64. And then finally, my second area, when you do the pi r squared, gives you 301. And that term in there is my shift 1, all squared. So it doesn't matter, you can see if shift is positive or negative because we square it. Anyway, plug in all this in your calculator, and I am sorry to say a small percentage of people get this wrong every year because they don't know how to use their calculator. So please, if you have time in the exam, stick it in once, then stick it in again and make sure you get the same answer. Make sure you square your shift terms. Okay, we have our moment of inertia now. And if we do go back to the original question, I won't, but I'll move on. But our original question, it told us that the yield stress in our plate was 750 MPa. Actually, I'm going to draw it here. And the yield stress, let me just check. I've updated this. Oh yeah? Sorry. Down here was 680 MPa. Now when we have bending, our bending stress distribution is triangular. So this is our bending stress distribution, and I really should draw it sticking out of the page. Okay, but I've drawn it side on there. It's 0 at the neutral axis. So it's a maximum at the top and the bottom. And because our section is asymmetrical, I haven't drawn that right, have I? No, because the top should look like it's a greater stress. So I did a really bad job on that. Oh. But I can fix it. And I'll just do that quickly while you're taking it all in by making this a lot taller. So now, does that stress at the top look bigger? So at the top and the bottom of the section going to reach the yield stress at the same time? No. Because this distance is bigger, the 65, you know that the stress at the top will be greater than the stress at the bottom. So let's calculate some stress values now. So the stress at the top in the plate, My on I, because my moment, if you go back to our bending moment diagram, it had the same maximum value of 10 and 10. We only need to check it at one location. So that would give me, I'm going to work in megapascals, so convert kilonewton metres to newton millimetres, times my 65, divided by the I value I worked out previously. And my stress is actually less than my yield stress. So therefore, I'm okay in the plate. So now let's check our stress in the bottom, in the square circular hollow section. I have the same moment, but I put in my distance to the bottom, and I get a stress of 651, which is less than yield stress also. So I am also okay. So overall, the section is sufficient. To carry the load. So hopefully that was a bit of revision after the break. Yeah? Okay. So at this point, we will pause and I'll tell you about the project. Now, first of all, I want to say that most of you did a wonderful job on Project 1. So you should all be very proud of yourself because, as I said, I do not know another university where after 7 weeks the students are actually doing real-life design. So you should all pat yourself on the back and be very happy. However, Monash isn't happy with your truss design. Well, they want you to look at other options. So even though they really liked it, the client, Monash University, fussy as they are, now wishes you to explore other design options. So instead of using a truss, they say trusses are passé. Let's just look at having beams span those distances. And you're asked now to look at 3 options. Excuse me, this diagram doesn't relate directly to yours, but because you can see signs here, this is the previous year where they have to do it with signage. They have to, at the Wellington Road entrance, put a sign over. Anyway, instead, now you have to consider the full span. See if you can get a beam to span the full distance. What did most people work out that full distance to be? Let's just say, let's call it 35 metres. So let's see if you can get a beam to span 35 metres, and that's pretty far to expect a beam to span. So now they're saying option 2, let's have an internal column, and now have your beam span, have 2 beams spanning 17.5 metres. So 2 simply supported beams. And now as your third option, we'll actually run 1 beam continuous. So here it's continuous over the centre support. So all of you are going to look at three options: full span, half span simply supported, and then half span continuous. Now, when I explain this now, I can't explain it in detail. Well, there is no point because as yet we haven't done all the theory. But anyway, as part of this investigation, this time round, you have to carry out a SLS, serviceability limit state check, as well as an ultimate limit state check. So in Project 1, you said per deflection isn't that important. We'll just do a strength check. Now, as well as a strength check, you have to do a deflection check because beams tend to deflect more than trusses. In Truss 1, Project 1, you actually said, let's just guess the members weigh 10 kilogram per metre, 15 kilogram per metre. Then you got to the very end, you worked out what they did weigh and said, well, I was conservative, we were unconservative. This time round, you have to iterate. You have to start off with a weight, do the calculation, actually calculate how big your member has to be, put that weight back into the calculation. The iteration comes out in 2 or 3 iterations. It takes no more than 3 iterations. Do the calculation again, check your member size. If it's the same member size, you've done, you've stopped. Otherwise, you have to go back and do it again. So we call that process iterating. And once again, you've been given initial beam weights to consider. And then finally, what you're going to do is you're then going to compare your truss design with your beam design, and you're not going to compare aesthetics because the beam looks pretty crap, okay? But you're going to compare it in terms of weight. So go back to your truss, calculate the correct overall weight of the truss, then compare it to how much these beams weigh, okay? And then do a comparison in that respect. Now, as well as that, and I haven't got it on here, ... there is a sustainability component that is very painless, where you're going to just walk around the campus and find 5 buildings and look at how you can improve the sustainability based on passive design. And I'm going to give you this really exciting lecture on passive design. And actually, I mean that sincerely because I think it's a really good lecture. Okay? So, when I say you have to do an ultimate limit and a serviceability limit state check, we know how to do ultimate limit state checks now. That means we're designing against collapse or failure. We use our correct load factors, which we did in Project 1. This time round, we're going to get our stress and just draw our bending moment diagram, stick it in our formula, and just make sure it's less than the yield stress. So it's easy enough to do. For here, don't worry about that, I'm not sure what that's down there. It was more complicated for the trusses. Here you're going to draw a simply supported beam, find where your moment is maximum, do an MY and I, check it's less than yield stress and you're okay. Bob's your uncle. Now as well as that, I will teach you on Wednesday how to actually calculate beam deflections. And what you will be doing is you will be calculating how much the beam deflects and making sure it doesn't deflect too much. So remember when we do serviceability limit state design, we use the same loads, we just put different load factors on there. So you're going to multiply your dead load by 1, your live load by 0.7, and then you are going to calculate a deflection. And you are going to compare it. A general formula is to compare it, make sure it is less than, for a simply supported beam, span on 250. So here is our span. Let's say our beam was 10 metres long. So if you had a 10 metre long beam, your maximum allowable deflection in here would be 10 on 250, which I'll turn it into millimetres, because when I turn it into millimetres, it makes it easy. That gives me a deflection of 40 mil. So when your beam is 36 metres long, that means if you divide that 36, turn it into 36,000 divided by 250, that will tell you your beam can't deflect more than about 150 mil. When you then halve the span, your beam can't deflect more than about 70 mil. So I'll be showing you how to do that, to actually calculate the maximum deflection in 2 days. So there's something to look forward to. Okay. So as I said, with the ultimate limit state design, you do an MY on I. Now, just to let you know, there is another term in those section tables. So, hang on. The sections you are going to be designing are not square hollow sections. You're going to actually come up with a universal beam section size. Now, when you look down the columns, once again, you have an area column, you have a moment of inertia, second moment of area column, and next to that is a Z column. And what Z is, it's effectively equal to I on Y. We call it the section modulus. So when you do your design, it's far easier to actually say stress M on Z has to be less than yield stress. So if you rearrange this, you can see the Z required has to be greater than or equal to my moment on my yield stress. You would then do that and find a value down here of Z bigger than what you require, and there's your design done. Boom. But what you would do, because you have to iterate, is come back here, work out how much the member weighs. Now, if you have forgotten, the designation for universal beams are usually given as a number, UB, a second number. That first number, 610, refers to the depth, and that second number refers to how much it weighs. So these beams are heavy. So you would then work out, choose your size, come across here, say my beam weighs 56.7. Oops, I assumed it weighed 30. So I have to go in now, recalculate my load, and do that calculation again. It doesn't take long. So that's the ultimate limit state design done. Now when we do our deflection check, well, first of all, let's go over why do we need, who cares how much it deflects? Well, there are a number of reasons, the main ones being, one, okay, to minimise perceptions of excessive movements by the occupants. You know when you walk on something, if it moves around too much, you are scared, you're not happy using it, so it's not usable, it's not serviceable. Another reason is that if we're in a building and the roof above deflects too much under wind load, well, what's going to happen? The ceiling's going to start cracking. And also, if there are any connected surfaces in there, pipes or cables, that movement could cause those things to fail. And finally, it's just a purely cosmetic reason. No one likes to see a sag. Okay? Saggy baggy. So we like things to look horizontal. And what we do, which we sometimes used to do in the project, if you have a beam that is sagging a lot, but you don't care, it doesn't matter, what we do is when we buy the beam, we say, could you please sell it to us bent, with a bend in it? And then under its own weight, it actually deflects down and looks flat. So we call that pre-cambering. Anyway, by the by. Okay, so on Wednesday I'm going to teach you how to actually calculate the maximum deflection. And then the formula for the maximum deflection is a function, of course, of the load, the span. So this is the span. These are the loads. And they are a function of Young's modulus, how stiff the material is, and my moment of inertia, my section modulus. So you can see, of all those variables, which one don't we know? We don't know our section modulus. So what we do is we equate our maximum deflection in terms of I to the allowable. So we actually say, let's equate the two. We solve for our moment of inertia, and then once again we come down this column here and we go across and we choose a size. So doing that, we end up with two sizes, one that's big enough for strength and one that's big enough for deflection. So which one do we choose, the bigger or the smaller of the two? The bigger. And there's your design done. Bob's your uncle again. There is a bit of a complication, which I won't go into yet, about the indeterminate beam because we haven't done the theory yet. So I will stop that presentation there, and I'm going to give you 5 minutes of deflection lecture. 5. That means we'll still finish 5 minutes early. No? Okay, we won't finish 5 minutes early because you're so unhappy about it. Bad luck. I'm going to give it to you now quickly, and again, when I go over it on Wednesday, it sounds familiar. It'll sink in better. Beam deflections. I love telling you how much you've learned because you've learned so much. You know all about loads. If I say dead load, live load, easy peasy, you know what all that is. Ultimate limit state, you know what all that is. You've just finished your truss. You have just finished your truss design, so you know how to design a truss. We're now effectively doing the same thing for beams. You know how to calculate a bending moment shear force diagram. You know the bending stress formula. You have to make sure that X is less than a yield stress. When we did trusses, we didn't look at how much a truss bent, but we did actually work out the formula for the squashing or stretching of an axially loaded member. Now we're looking at beam deflections. Come on, give me 5. Give me 3. You can all, at 5, 4, 54, say stop, but you're not allowed to look at the clock, you have to look at me. Okay, so when we design a beam or any structure, we have to consider serviceability requirements as well as strength requirements, and the main serviceability requirement is deflection. What are the other serviceability requirements, you may be asking? One would be vibration, if you're building a sports floor. Another serviceability requirement would be fire loading. So your structure, all structures have to be fire safe up to a certain amount of time to give people enough time to vacate the building. So you also have fire as a serviceability design. We're going to limit ourselves to deflection. I've already been through. Why is deflection important? Because we want to minimise perception of excessive movements. We want to limit unsightly appearance of sagging. Shush! Shh! I've got 2 minutes left. And we want to ensure attached surfaces don't get damaged. Now, there are different deflection limits depending on the situation we're dealing with, but deflection limits are set according to span, and they vary depending on their purpose and location. So if you're dealing with a floor, you would just ensure the live load deflection was less than span on 250 or span on 400, depending on the situation. That's for timber. If you are looking at the roof rafters, on a roof you don't get a lot of live load. So it's more important that under dead load it doesn't deflect too much. Because if you have a permanent sag in your roof, especially if you have a flat roof, you get water ponding on your roof. Never build a flat roof, by the way, unless you know a really good waterproofer. Okay? So if you had a very big dead load deflection on a roof, the water will pond there and sit there and your roof will become damaged. If it deflects too much under live load, under wind load, well, who's up there to see that? So the deflection criteria is one for dead load. For a floor, because it's live load walking on your floor all the time, deflection criteria is live load. In this subject, we're only going to consider one loading, and that is your dead load plus 0.7 live load. So we're going to say with that combination of loading, it can't deflect for a simply supported beam more than span on 250. If you're dealing with a cantilever here that deflects like so, the limit usually is that this deflection here has to be less than your span on 125. And span is, of course, well, the distance between supports, or for a cantilever, the length of the beam. Okay, no one yelled at me. Oh, you're so polite. Okay, we'll stop there and I'll see you all on Wednesday.